All right, this is Unit 8, Notes 1, Part 3. This will be our last discussion, our last lecture for Notes 1. We're just going to begin by reviewing one more time the electromagnetic spectrum and kind of relating the size of the waves to things that we are familiar with. So, a radio wave is on the lowest end of the electromagnetic spectrum, if you recall that. And these waves are actually very long. So, how big are they? Well, the longest ones can be about the size of buildings, they're absolutely massive. Um, There, from crest to next crest, that's one wavelength. Recall that from Unit 7. Those waves are can be 100 meters plus in size, and they could also range to about 1 meter size, so like the size of a human or like a small child. So those are going to be radio waves. These are considered to be very large waves in comparison to all the other ones, and therefore they're going to have low energy. A microwave is going to be much smaller. Microwaves are about the size of a honeybee, so you can see just, a centimeter or so. Infrared waves are pretty small as well. They are about the size of a pinhead. So right here, like the size of this pinhead, um, again, getting much smaller. Visible light is actually very small. It's the size of little tiny organisms called protozoans, so no bigger than that. So visible light is very small. And then we start to get to ultraviolet light, where we start to see they're the size of molecules. So those ultraviolet uh, waves, they're really small. X-rays are like the size of atoms, and then gamma rays are the size of atomic nuclei. So just the nucleus of that atom right there. So once again, we're starting to see that from going from radio waves all the way to gamma rays, we're going from large waves to small waves, a large wavelength to a small wavelength. The frequency, so we're talking about this relationship again between wavelength and frequency and energy. The frequency is going to be very low over here, 10 to the fourth, right? In comparison to over here, 10 to the 20th. So that frequency for gamma rays is very high. And then finally, we have energy here, 10 to the negative 10th eV versus 10 to the 6th. You can see here that this has a lot more energy than any other type of wave here. Um, so gamma rays, for that reason, are very dangerous because they can not only contain a lot of energy and can enter our bodies, they can mutate the nuclei in our cells, in our DNA, and kind of mutate and kill our cells. So they're very dangerous. All right. Continuing on here, we have the colors of the visible light spectrum. So, going back to the electromagnetic spectrum, actually, let's move on to the electromagnetic spectrum. Just recall here that out of all of the rays here, this tiny little band is all that we can see. That's the visible light. So, going back to this chart here, all of the visible light here, if we were to expand it and show you what the wavelengths look like, red has the largest wavelength and has the lowest frequency and the lowest energy. Over here, violet has the shortest wavelength, highest frequency, and highest energy out of all the lights. So just recall that the different colors of lights do require different amounts of energy, or do have different amounts of energy. And violet's going to be the most intense, and red's going to be the least intense. All right, so the electromagnetic spectrum, what we're going to do is just discuss each single type of wave and what their purpose is, and just more properties about that. So radio waves, like you mentioned before, they're the longest wavelengths of the electromagnetic spectrum. We use them for AM and FM radio communications, and we also use radio waves for radar. And radar is actually an acronym, stands for radio, detecting, and ranging. So that's what radar stands for. And we use it for MRI, so magnetic resonance imaging. I'm going to go ahead and actually hide here so that you don't see me. There we go. So MRIs use radio waves. So if you know what an MRI is, or if you don't know what it is, it's basically a fancier version of an X-ray. They put you in this machine and they can see not only your bones, but also your body tissue on the inside. So we use radio waves for that. Microwaves, they have a wavelength of 0.1 meters to 0.001 meters. So they can range from visible to really small. Microwave ovens heat food by vibrating water molecules, and this only occurs with a very specific wavelength that is the distance between oxygen and hydrogen atoms. So microwaves, the way they work, there's a specific wavelength that goes up and down, and that wavelength fits perfectly between the oxygen and the hydrogen atoms of a water molecule. And so what it causes the water molecule to do is shake back and forth. It's like basically shaking that water molecule violently on an atomic level to the point where that water molecule is now generating a heat. And so when it's generating heat, it's going to start heating up your food. So that's the way a microwave oven works. We also use microwaves for satellite communications and GPS systems. So like I mentioned before in a previous lecture, I believe it was Notes 1 Part 1, I mentioned that our phones use microwaves in order to communicate. So like GPS and satellite communications, our modern smartphones have microwaves that are used for communication. And yep, so I mentioned cell phones there. And then let's talk about infrared waves. So infrared waves are waves that carry thermal energy as heat. So infrared is just underneath visible light, right? So keep in mind there are animals that can see infrared, like some birds and some reptiles can see infrared waves. And what that basically means is that they carry thermal energy or heat. So anything that has heat is basically going to be giving off infrared waves here. I have a picture down here of like a thermal imaging of a house, and this might actually be useful for someone who's trying to upgrade their windows in their house. Let's say you notice that your heating bill is really high every winter, and your cooling bill, like your AC, is running a lot during the summer. Well, I know some energy companies, you can actually call them over and they'll do like a heating assessment, energy saving assessment on your house. And what they'll do is that they'll take a little instrument and take a picture of your house like this, and they'll actually use a different sensor to detect the infrared waves. The infrared waves will be coming off, and if there's a lot of heat escaping from your windows like it is here, that means your windows are not very efficient, or maybe that wall's not very well insulated. So what they'll recommend is that you actually tear out those windows and put in some new ones. So that's actually a really great technology that we can use to kind of do a heat assessment or an energy saving assessment on our homes. We also use infrared waves for remote controls. I mentioned that before, so that you can use a remote control for your TV or your stereo or something like that. Those have a little infrared bulb at the end of them. And then thermal photographs, like I mentioned before. Visible light, we already covered, so we're just going to skip that and go on to ultraviolet radiation. Ultraviolet waves can cause sunburn and skin cancer, but are also needed for skin to produce vitamin D. So humans don't actually need to ingest vitamin D. We can actually produce our own. The only thing that we have to do is to go out into the sun. But up here, where we live in Minnesota, we actually have issues with many people not being able to go out during the winter, and we have limited sunlight. So a lot of people get vitamin D deficiencies during the winter, but in the summertime, we don't have to worry about that. So a lot of times, sometimes you'll see like orange juice or milk that has vitamin D inside of it. And that just basically means that you should probably be taking that during the winter in case you're not getting enough sunlight to generate your own vitamin D. You can have too much vitamin D, so you should not be taking vitamin D supplements. As long as you're going outside and don't have any medical conditions, you should be getting enough of that. Ultraviolet waves can be also used to kill bacteria. I know a lot of times in science classrooms, we have these goggle cabinets that have an ultraviolet light bulb inside of it. It's a light bulb that generates ultraviolet waves. So every single time the goggles are being used in the class, we put them in the goggle cabinet, and then we turn on this timer, and the timer actually turns on the light bulb for like, let's say 10 minutes or so, and it releases ultraviolet waves, and it kills all of the bacteria on the goggles. So that's a really useful situation where we can actually just kill a whole bunch of bacteria at once without having to wipe down a whole bunch of equipment. X-rays are next, and you guys know what X-rays are used for. They can travel through soft tissue like our muscles and our skin, but are stopped by bones to make medical X-rays. So like over here, you can take an X-ray of a hand or different bones, or sometimes like you have to go to the dentist and they'll take an X-ray of your teeth. That's basically what we use X-rays for, nothing more than that. But we also use them in airports to inspect luggage. I'm sure you've seen like the TSA images of like they scan your luggage or your bags to make sure there's nothing harmful in those bags. Finally, gamma rays are ultra high frequency. They're high energy waves that can break molecular bonds. If we're very careful with them, with the gamma rays, we can actually use them as radiation therapy to kill cancerous cells. But if we don't control that, they can also kill healthy cells. So we have to do that very carefully when we do gamma radiation therapy. This is a new-ish technique that kind of replaces chemotherapy for a lot of milder cancer patients. So radiation does help a lot of people, and you don't have to go through the process of taking chemo drugs there. Okay, so now what we're going to do is take a look at practice problems 11 through 15. So let's go ahead and do that. All right, so here's practice problems 11 through 15. We're going to run through these pretty quickly. Number 11 is a matching section, so we're going to start off with number 1. Electromagnetic waves that give off heat. Which type of wave from the electromagnetic spectrum was this? The answer, of course, was B, infrared waves, so they give off heat. All right. Number 2, electromagnetic waves that can carry telecommunication signals and cook food. So those are the two things here. They have signals, telecommunication signals, and the ability to cook food. Those, of course, were microwaves. So that's E. Electromagnetic waves with a high energy that can cause sunburn. Well, you know that these come from the sun, and they're going to be ultraviolet rays. So A. Electromagnetic waves used in medicine to kill cancer cells and view bones. So those are going to be two specific types of rays, and they're going to be X-rays and gamma rays. So F. Number 5, electromagnetic waves used for television, AM, and FM radio signals. Well, the word radio should throw you off here, so it's going to be D, radio waves. And then finally, electromagnetic waves used to determine the location of an object in a room. Well, we use visible light to determine the location of the object in a room just by using our sight, right? So if there's light in a room, we can see it, and when we can see stuff, we can locate them in the room. So that makes sense. C. All right, number 12. Number 12 says, which of the following uses radio waves to find an object's location? So we're using radio waves to find an object's location. So is that sonar, ultrasound, sonogram, or radar? The answer, of course, is going to be radar. Because radar is an acronym that stands for radio, distancing, and ranging. So don't forget that. All right, problem number 13 is a word problem, and it says find the color of light whose frequency is 5.21 times 10 to the 16th hertz. We're going to start off this problem by doing what we do in all other word problems, and that is to write down whatever is given to us. So frequency was given to us, and that is 5.21 times 10 to the 16th hertz. Now that was all that was given to us in this problem. And what is the problem asking for? It says find the color of light. Well, there's no real unit for the color of light, but we did learn in the notes that color of light is correspondent to a certain wavelength of light. So what the question is asking for is like, what is the wavelength? All right. So the color of light corresponds to the wavelength, and it says find the, so we can pretty much just substitute the word wavelength for color of light. Find the wavelength whose frequency is 5.21. All right. Is there an equation that associates frequency and wavelength? Sure there is. It's C is equal to frequency times wavelength. All right, and we should know C, so we're going to put that down in our known data column here. And you know that it's 3.0 times 10 to the 8th meters per second. Right? And then we have to find what wavelength is. So what I'm going to do is rearrange this equation so that we are solving for wavelength. So that's going to be equal to C divided by F. One thing that I've noticed in this problem actually is that this won't actually give us a color of light. This will give us a wavelength of light that we actually can't see. There's an error in this. So I'm going to just make a note here. And I'm going to erase this 10 to the 16th. And it's actually going to be 10 to the 14th. So let's go ahead and write that down. So that will actually be a visible color. So it's 10 to the 14th. So let's go ahead and make that change now. And so wavelength, I'm just going to go ahead and start plugging these numbers in. So going from here to here, we have 3.0 times 10 to the 8th. That's going to be our C, and then divided by 5.21 times 10 to the 14th. And then what we need to do is start dividing scientific notation. So what I'm going to do is first step in scientific notation division is to divide these guys like normally. This is called the mantissa again, if you forgot. So you divide that together. So you do, I'm just going to punch this into my calculator. 3 divided by 5.21. I get 0.5758. So I'm just going to round to 0.58. or let's do 576. All right, we could do 576 times 10 to some power. Well, what you're going to do with division in scientific notation is just subtract these. So 8 minus 14 gives us a value of -6. Okay, and that gives us a wavelength. That's not true scientific notation. True scientific notation means that the mantissa, or this front number here, has to be between 1 and 10. So I'm going to write this down as 5.76 because that's between 1 and 10. And then that means we did move the decimal over one spot. So when we did that, it changed the exponent as well. So it's not 10 to the -6, it's 10 to the -7th meters. So we can write that down right now in our solution panel, but that's not our actual answer. I'm just going to write that down here. Times 10 to the -7th meters. All right. The question was asking for find the color of light. So we're looking for a color. Well, there was a graph in our notes that corresponded wavelength to color, and it looked like this. I'm going to go ahead and expand this out right here so that we can see this. Now these numbers here, they're in hundreds, right? So this is a 5.76, and the range here is from 400 to 665. And the unit here is meters, and the unit here is nanometers. Well, you guys should know that 1 meter, or it's the correspondence between meter and nanometer is a nanometer is 10 to the -9th meters. So 1 nanometer is equal to 1 times 10 to the -9th meters. Okay, so we're getting a little bit closer by changing our meters to nanometers, but what we need to do here is change this so it's 10 to the -9th. In order to do that, we need to move the decimal over 2 more times. So the wavelength, if we move this decimal over 2 more times, it'll be right there. It's 576 times 10 to the -9th meters. Or another way we could say this is 576 nanometers. Okay. So now we want to take a look at this chart to kind of correspond that to a color. It's somewhere in between green and yellow. So 550 is going to be green and yellow is going to be 600. So what I'm going to say is green yellow. That's the color of light that is given off by this specific wavelength. So there's the answer for number 13. Number 14 is a multiple choice. It says determine which band of the electromagnetic spectrum has the following: the lowest frequency, the shortest wavelength, the most energy, and the least energy. So it's actually not a multiple choice. It's just multiple parts to it. So which one has the lowest frequency? Which one's going to be least often? It's going to be radio waves. Which one has the shortest wavelength? The band on the electromagnetic spectrum that has the shortest wavelength is going to be the gamma rays. Gamma. The most energy, once again, is going to be gamma. And you should know this because we're associating shortest wavelength with the most energy. So short wavelength, high energy. Again, just re-emphasizing that point. And the least energy, well, least energy is correspondent to lowest frequency, so the answer there is radio. Okay, so we have radio, gamma, gamma, radio. And finally, number 15. Determine if the following statements are true or false, and then explain your answer. Photon energy increases as wavelength increases. I'm going to go ahead and switch the typing tool here so that I can just type out the answers instead. And I just want to make sure, okay, that's a good size font. Does energy increase as wavelength increases? This is false. Let me change this to red so you guys can see this actually. Okay, so false. Energy increases as wavelengths decrease. So if the wavelength is getting shorter, the energy is increasing. All right, photon energy increases as intensity decreases. This is actually true. So the closer you are to, let's say like you're shining a flashlight, the closer your object is to your flashlight, the more energy you're going to be able to shine on that object. So let's say you're shining a flashlight on something that's directly on the ground right in front of you. You can see that very well. But if it's something that's like half a football field away, like it's 50 yards away, you're not going to be able to see it very well. So the intensity will decrease. That means the photon energy is going to increase. All right, photon energy increases as frequency increases. This is true. And that means letter D, of course, has to be false. And we're going to explain energy increases as frequency increases. So just remember that relationship that we've been talking about ever since Unit 7. I've mentioned it several times. Just recall that information. All right, so that concludes practice problems for Notes 1, and that concludes Notes 1 altogether. We'll see you again when we get to Notes 2.